Well, hey students, it's Mr. Rich. Sorry to keep you waiting. It's about 7:04 on Sunday, May 11th. We're getting ready for the AP Precalc exam this coming Tuesday. And what I'm going to do today is we are going to work through some problems that I predict you're going to see that you need to know how to work for this exam coming on Tuesday. I've got 10 problems that I've selected, and we're going to work through these over the next hour. I think we'll be able to get them all in, and I have a few bonus ones at the end. So let's get right to it. And here we go. So I've got Desmos up. And, you know, one of the things that you have to consider as you're getting ready for the test this Tuesday is, are you going to be using Desmos primarily, or are you going to be using your graphing calculator? Definitely take your graphing calculator with you, but I think that a lot of the things that you do on this test, you should probably be using Desmos, because whatever you can do on your TI-84, Desmos can do it faster and more efficiently. But having said that, if you haven't used Desmos much and you're not all that familiar with it, and you're more comfortable with your calculator, probably stick with that. But I am going to use primarily Desmos here tonight to give you a flavor of what it would look like. Okay, so let's jump right in. So the first problem that I think that you're going to see, and I discussed this with another student earlier this week, I think it might have been yesterday or the day before, was a problem involving missing coefficients in a logarithmic real-world function. I kind of think that this year they may change it up. They put a problem like this, similar to this last year. I could see them doing a problem like this with an exponential function, but I'm going to use one that is a logarithm, which is kind of similar to what they did last year on the free response questions. And again, if you're just joining us, my name is Mr. Rich. We are looking at some AP Precalc problems that I predict are going to be similar to what you're going to see on the test this coming Tuesday. If you do have any questions, I do keep my eye on the chat here in hey Parv, I'm glad you are here. But I'll keep an eye there to see if you have any questions as I go through this. All right, so the first question here is 20 people interested in alcohol use and the amount of alcohol in their bodies over time participated in a 2-day-long study to observe how much alcohol they retained in their body over time. After consuming a certain amount of alcohol based on their weight and other body conditions, participants underwent an initial blood and urine test to determine their blood alcohol level. At that time, t equals 0, all participants were measured to have approximately 0.15% blood alcohol content. And then for the next 48 hours, the group was retested every 6 hours to track their alcohol levels. After 6 hours, t equals 6, the group's average BAC was about 0.09%. So it went from a 0.15 to a 0.09. If the group's average BAC percentage can be modeled by this function, where f of t is the average BAC percentage, right? So I'm going to drop the percent signs here. I'll be using those numbers, 0.15, 0.09. For hour t, and t is the number of hours since the initial test. First question here says, use the given data to write two equations that can be used to find the values for constants a and b in the expression for f of t. Well, they just want us to take two ordered pairs, basically. We have an ordered pair of when time t is 0, the BAC was 0.15. And then when t is 6, it was down at 0.09, like that. So what we're going to do is plug in each of these ordered pairs. So the very first equation for my Roman numeral 1 is going to be 0.15 is equal to a plus b times the natural log of 0 plus 1. The other one is going to be, at the other time, t equals 6, the BAC is down to 0.09. And that's going to be a plus b times the natural log, and t is 6, so that's going to be 6 plus 1, or the natural log of 7. Okay, hi Ethan, good to see you here, buddy. All right, so there's my two equations. That is my expression, my answer for A1. Now, number 2 says to go ahead and find those constants A and B. So I'm going to solve this as a system of equations. Now, I've got two options here. I could use my calculator. I could use a TI-84. I could use Desmos. Now, one of the problems with the TI-84 is the way that I've written those two equations is that they are not written in explicit form. In other words, one of the variables is not isolated on one side. I could easily do that, right, by solving for A on both of these. But here's the beauty of Desmos. Desmos does not care how you write the equations, whether they're explicit with y isolated on one side or y's and x's all mixed together. It doesn't matter. So what I'm going to do here is I'm actually going to solve this by graphing. So I'm going to graph the first equation. Now I'm going to use x's and y's instead of a's and b's. So I'm going to do 0.15 equals x plus y times the natural log of 1. Okay, and that's what that looks like there. Now let's do that. Okay, now why is that a vertical line? Well, what is the natural log of 1? The natural log of 1 is 0. So we know what A is. So we could really do this with using algebra really super fast, but we'll do it by graphing. 0.09 is equal to A plus B ln of 7. And that needs to be x and y, doesn't it? So x and y. Okay. And then we're going to zoom in like crazy and to see where we are intersecting here. And there's our point of intersection. So no surprise, A was 0.15. I kind of knew that because that was going to be a 0. The natural log of 1 happens to be 0. But that does tell me that A is equal to 0.15 and B is equal to negative 0.031. All right. Now, this is a calculator active question. So it's not telling me, does not say that I need to show my work or how I arrived at those answers. Now, how would you have done this if you're just doing a pure algebra solution? Well, really what happens here is right away, based on this equation, for the fact that the natural log of 1 is 0, you know immediately that A is 0.15. So you've solved half of the problem there. You could then come down and plug that value into the second equation for A. So you get 0.15 plus B times the natural log of 7. Then I would be over in Desmos, and I would say 0.09 minus 0.015. Let's try that again, 0.015. Okay. So I'm subtracting that over. I get that answer 0.075. And then I would be dividing that by the natural log of 7. And now let's see, that doesn't look like it gave us exactly what we wanted. That's because I subtracted 0.015. 0.15. There we go. Which is negative 0.06. Which doesn't make sense. Let's go back. 0.09. Here, A is 0.15. So we have 0.09 minus 0.15. Yeah, no, that makes sense. So then what that means is I'm taking my negative 0.06 and then I'm dividing that by the natural log of 7. And there's my answer for B, which was a negative 0.031. All right, so that's what they want you to do. Now, here's a mistake I think that was made last year on this test, is that some students interpreted this to mean to use regression to find out these values for A and B. They did not want you to do that. They wanted you to actually use either a graphical method that I just did or an algebraic method by substituting the two ordered pairs that they gave you. All right, if you have any questions, post over in the comments section of YouTube if you're watching on YouTube. All right, let's go down to the next question here. Now, this is the second part of that FRQ, but it's what I'm calling problems 2 and 3 for tonight, is you can expect to do an average rate of change in context using a secant line. And then also use concavity to compare average rates of change. So I'll show you what I mean by that in this second part of this free response question. And again, my name is Mr. Rich. We're doing AP Precalc. If you're just joining us, we are working through 10 problems that I predict are types that you will see in Tuesday's AP exam. This next part says, use the given data to find the average rate of change of the blood alcohol concentration percentage in percentage per hour from t equals 0 to t equals 6. Express your answer as a decimal place. Okay, strange. Show the computations that lead to your answer. So they want us to show what we are doing to get this answer. So what I recommend here, students, is that when you're showing the grader your work, you're going to say average rate of change. I'm going to write that out, average rate of change, and I'm going to say t equals 0 to t equals 6. Okay, now what I'm going to do is I'm going to show the typical average rate of change calculation to the grader to show them what formula that I used. And what I'm doing here is I'm using this function that we have, f of t, and I'm going to write it like this. I'm going to do f of 6 minus f of 0 over 6 minus 0. That is an average rate of change calculation. This is the change in the y value of the function. This is the change in the x values over that given interval. All right, and so then what we're doing is we're going to find f of 6 and f of 0, but actually we already know what they are because they gave them to us, right? F of 6 was 0.09, so we're going to put that in. So we're going to show to the grader that we substituted 0.09 for f of 6, and f of 0 was 0.15. And 6 minus 0 is 6. Then we're going to go ahead and do that calculation. So it's a negative 0.06, and then we'll divide that by 6. We get negative 0.01. Notice that they say, yeah, they want it in percentage per hour. Now, these are percentage points, and these are hours, right? So the units here are percent per hour, negative 0.01% per hour. Express your answer as a, I'm not even sure what that means, as a decimal place. But at any rate, we are always rounding out to the third decimal place in any of our calculations here that we're doing with our calculator. And that's going to be just out to 2 decimals because it is a perfect negative 0.01. All right, the next part says interpret the meaning of your answer from one in the context of the problem. So what my answer to this is going to be, and I'm just going to speak it here. I'm not sure. Maybe I can type it out a little bit faster. So it's going to look something like this. I'm going to say from t equals 0 to t equals 6, blood alcohol concentration percentage decreases, right? Because it's a negative average rate of change. Decreases by an average of 0.01% per hour. That's it. All right. I'm just saying that that is the rate of change. It's decreasing. Do not put decreasing by a negative. The negative itself is the indicator that it is a decreasing. If you changed this and said it changes by an average of a negative 0.01, that should be acceptable. But it's better to just say that a negative is a decrease. If it was a positive, it would have been an increase. And then the last one here, it says, and this part 3 is this problem number 3. I'm saying using concavity to compare average rates of change. It says, consider the average rates of change of the function f from t equals 6 to t equals m hours, where m is some time after 6. Are these average rates of change less than or greater than the average rates of change from t equals 0 to t equals 6 found in 1? Explain your reasoning. Well, what they want you to know, what you should know, is that since this is a natural log function, it does have a, let's see, we have to be careful here. What I'm going to do is we're going to graph this function. Let's graph it because we know what a and b is. So we're going to graph f of t. So that's going to be 0.15 plus, or actually it's going to be a minus. It's going to be a minus 0.031 natural log of x plus 1, like that. And then we are going to take a look at it, what it looks like. All right, so that's kind of why I'm glad that we graphed this thing. So it is a log function that has a vertical shift of 0.15, but it also has a negative in front of the log, which means it was reflected, right? Normal log functions, just regular y equals natural log of x, is a concave down function that increases but then slowly decreases its rate of increase. So it's concave down, it looks like that. But because of the negative that we had for the b, that was the coefficient in front of the logarithm, it's been reflected. And so it's actually coming down like this. So that means it's concave, it is concave up, is what that is. So, but it's concave up and it is decreasing. So what our answer is going to be here is, what is the average rates of change? What happens here is this, class, is that if you take a look from, say, 0 to 6, the average rate of change is going to look like this. But down here, the average rates of change are going to be less negative. So they are increasing. Think about that. This is a negative value, but this is negative but less negative. So they are increasing. To become less negative means to increase. And so what is our answer going to be on this? It want to know, are these average rates of change less than or greater than? They are going to be greater than. So we are going to say the average rates of change for t greater than m will be greater than those from t equals 0 to t equals 6, because the function f of t is concave up, and thus the average rates of change are increasing. Okay, so the concavity is telling you, as you move left to right, whether the average rates of change are going to be going up or going down. All right, if you have any questions about these, let me know. Or if you think I'm wrong, let me know. That is questions 2 and 3. Let's go to question 4. You definitely can expect to solve trig equations using the Pythagorean identities. You will see these in both multiple choice and free response. It's almost a certainty that you will find a free response question. You've seen probably enough examples as you've been working in your classes that they typically like to give you an equation from unit 2, which is either a log or an exponential, and then also one from unit 3, which is a trig equation. And then they ask you to solve it or simplify it. So, but here's a variety of that comes from a multiple choice question. It says, what are the values of x on the interval 0 to 2 pi, where 2 cosine squared x equals sine x plus 1? Well, if I'm going to solve this, I do need to get this cosine squared changed into the same trig function as the sine x. And the way that I'm going to do that is I'm going to use the one trig identity that we use the most when it comes to changing sines and cosine squares. And that is that sine squared plus cosine squared, right? Sine squared of an angle plus cosine squared of an angle is equal to the number 1. So therefore, cosine squared is 1 minus sine squared. So on my scratch paper, right, this is multiple choice. You're going to work this on your scratch paper. You'll be seeing this problem on your screen, on your device in Blue Book. So it'll be 2 times 1 minus sine squared x. There's my substitution right there, equals sine x plus 1. I'll distribute the 2, and we'll get 2 minus 2 sine squared x. At the same time, I'll go ahead and bring the sine x to the left. and bring the plus 1 over to the left, and it looks like this. Now I'm going to put this in descending order of power. So I'm going to put -2 sine squared x minus sine x, and then 2 minus 1 combines to be a positive 1. So this ends up being one that I'm going to factor into the product of two binomials, just as though it was a quadratic. But I never want to work with these equations like this where my leading coefficient is negative. So we're going to multiply all the way through by a -1 so that it will look like this. And then we're going to factor this into the product of two binomials. That means that this has to be a 2 sine x, this has to be a sine x. Well, because this is a -1, that means that I'm going to put a +1 and a -1 right there. Okay, and I know that that's the way I want to put the plus and minus, and the quick check, again, is to see whether I have the right middle term. If you look at the outer product, that's a positive 2 sine x. The inner product is a negative sine x, and those two combine together to be positive sine x, which is what we wanted in the original trinomial. So then what we do is if we have two factors in our expression and we've got 0 on the other side, the only way this equation is going to be true is if either one of those factors is equal to 0. So we are going to solve these two equations separately. So this is going to be sine x is equal to 1/2. This is going to be sine x is equal to -1. So this requires you to know your unit circle. Where is sine going to be 1/2? That's going to be in the first and second quadrants, pi over 6 and 5 pi over 6. -1 is for sine. Again, we're only looking in this interval right here. That's going to be at 3 pi over 2. So it looks like there's only 3 solutions to this. And let's see, how are we doing here? Sine. Do we have that? I don't like my answers. No, this is it right here. Yeah, we got it. D is our answer right there. Okay, that is problem number 4. So make sure you know your identities, right? I mean, this is crucial. If you don't know these identities, I've got them over here. I've got more than we need here, but the identities that you need to know for Tuesday are for sure these Pythagorean identities right here. You need to know all 3 of those. The one that you're most likely to use is the first one here, sine squared and cosine squared being 1. There's still a decent chance you'll have to use one of those two somewhere along the way. And don't forget that as long as you memorize this first one, these other 2 can be derived from the first one. Because if you take this equation and divide all the way through by sine squared, you're going to get this one. If you divide all the way through by cosine squared on both sides of this equation here, you will get that one right there. Okay, so you can derive those other 2. The other identities that you need for the test, you do need to know the sine and cosine double angle, don't need to know the tangent double angle, but you do need to know all 3 of these, right? The sine double angle, there's only one option right there. It's 2 sine cosine. And then on the cosine 2 theta, if you memorize this one, these 2 can be derived by combining this one with the Pythagorean identity, where you substitute in for cosine squared and sine squared. So these 2 can be derived from this along with the Pythagorean identity. All right. Also, just one quick tip here. You got to also be on the lookout for sometimes problems are going to require you to use this identity backwards, right? You might at some point possibly have to recognize this and then come back to rewrite an expression as sine of twice whatever this angle is. So you are always thinking about on trig functions where you're simplifying or solving by doing substitutions. And then there's one other set that you most certainly are going to be using probably more than once. And that's going to be the sum and difference formulas for sine and cosine. So make sure you use these. I don't think I have one of my 10 questions that I'm showing tonight using these. I don't believe I do, but these are pretty straightforward as long as you know it. Now, as long as you know these formulas. Be on the lookout, right, for problems that look like this, that sometimes students don't recognize that they're supposed to use the sum and difference formula, right? If you see an expression, sine of x plus 3 pi over 2, you're going to be using this formula right here to break this out. And so even though one of them is a variable and one of them is a fixed angle, you still are going to use that sum and difference formula to break it apart into both x and 3 pi over 2. All right, so let's go back to our next predicted problem. Problem number 5, exponential modeling with change of time units. These give students fits, and I wanted to go over one of these with you. So this says that lead has a half-life of 30 days. I guess that's true. I didn't know that. That can't be true, but I guess it's true. They wouldn't put it in if it wasn't true. If in a particular sample, the amount of lead remaining after d days could be modeled by the function f of d is p0 1/2 d over 30, where p0 is the amount of lead in the sample at time d equals 0, days equals 0. Which of the following functions models the amount of lead remaining after h hours, where p0 is the amount of lead in the sample at time h equals 0? So they're switching the units of time from days to hours. Now, when I look at the function, I do notice that they didn't change the fact that we are multiplying by 1/2, right? So this becomes pretty straightforward. So think about what this means, right? If you showed me this formula right here, I would know that the half-life is 30 days without them telling me. Because when will this first 1/2 to the 1 power be applied to the initial amount of lead? It would be applied whenever the value of d, the variable d, takes a value that would make the exponent a 1. And that's obviously when d is equal to 30. When d is equal to 30, the amount of lead is going to be the initial amount times 1/2 to the 1 power. And so therefore, that would be the first 1/2 multiplier applied there at d equals 30. So really what we know is that, or what I'm considering is, if you're going to change it to hours, I'm just going to say, well, you know what? How many hours are there in 30 days? So 30 times 24 is 720. So I don't want the first 1/2 multiplier to be applied until h reaches a value of 720. Okay, and you can see this is going to be my obvious answer, because I want this exponent to be 1 at day 30, so that the first 1/2 multiplier gets multiplied by the initial amount. Now, what they do on the SAT, because they put problems like this on the SAT, typically what they will do is they will make another answer choice 720 over h in the exponent, and try to get you to go for that by saying, oh yeah, when h is 720, that'll make me an exponent of 1. Yeah, but that's not going to work, because when you go to values greater than h, then you're actually making the exponent reduce, right? So you don't want that. So it's got to be h over 720. Okay, so there's more to say on that one about the fact that this is really going to be what we call a horizontal stretch. It's a horizontal dilation, but I don't really want to get into that. We don't have much time to talk about that. Okay. All right, let's move on. Problem number 6. It's about 7:30, and my name's Mr. Rich. If you're just joining us, we are doing AP Precalc problems. I'm doing predictions of what I think are likely difficult problems that you're going to see on the test this coming Tuesday. If you have a question about what we're working on here, or if you see me doing anything that you're not sure of what I'm doing, or if you think I did something wrong, post a comment over in the comments in YouTube if that's where you're watching. Next problem, linear regression. This would be one that you would be using your TI-84 or Desmos. Now, I'm going to make the case here that Desmos is superior, and not just by a little bit, by a lot. All right. I love my TI-84. And I loved it a lot more before Desmos came around, and we started using Desmos a lot. I mean, Desmos has been around a long time, but as soon as SAT went digital a couple of years ago, and we started training students to use it on their SAT, then I realized, this makes total sense to use it in AP Calc and AP Precalc. Not so much for AP Stats because it's got limited statistical functions as compared to the TI-84. But this says, the list in the table above shows the annual incomes of a certain professional over the years. Which of the following equations could be a linear regression model for the data? Well, the data is increasing. I'm just not going to do too much work here. It's a calculator active problem. So what I'm going to do in Desmos is the following. I'm going to put the table in and then run the regression. So I'm going to hit the plus sign. The only time you're going to hit that plus sign in Desmos is if you're going to be adding a table. So we put the table in there, and then I'm going to use my finger on my left hand on the tab key, and I'm going to hit the cells, hit the tab key to jump from cell to cell. And so that allows me to go pretty fast to type things in. And of course, I'm going to check this at the very end to make sure that I didn't make any errors. All right, so I'll double check this. 1358 1220, that looks good. 45, 65, 73, 3, 91, 110, 210 looks good. This icon right here, students, it says add regression. Click that. It defaults to a linear regression. If you were supposed to do like a quadratic or a cubic or an exponential or a logarithmic or a power, whatever, sinusoidal, you can even do a custom regression, which if you're doing the SAT, I would show you how to do a custom regression, but you don't need to know that right now. But look, it spit the equation out for me right there. I know that my answer is, do I know what it is? 8240, yeah, so it's going to be A. It's the exact answer right there. Okay, so just dump that right in there. I can make the case that I can do this in about certainly less than half the time it would take me to do a linear regression on the TI-84. Okay, so that's it. That was pretty easy. Problem 7. I predict you're going to be doing an exponential growth where you have to find a growth and decay constant. This also would be an exponential, a calculator active problem. So what they do is they give you a function h of t, and they are asking us to find, well, no, they're not asking us to find k. They just say k is a constant. But they do, am I zoomed in too far? Yeah, okay, there we go. Wait, something's missing here. It says if h of 10 is 225,000, yeah, thanks. Thanks there, Ethan. Appreciate it. Okay, on the lead. If h of 10 is 225,000, what is the value of h of 15? So what they're not telling you, but what you have to do is you've got to plug this ordered pair into the function and then solve for the decay constant, k, right there. Have to do that. So I'm going to plug the 225 in here for h of t. So it's going to look like this. It's going to be 225,000 is equal to 750,000 over 1 plus 0.45, and t is 10. So this is going to be 10k, and I'm going to solve that for k. Now, I can do this pretty quick algebraically, but I am not going to do it algebraically. I'm going to solve for k by graphing the left-hand side of the equation. 200 y equals 225,000. Now, where is that? That's way up there. I don't have to tell you that, right? Y equals, we're going to get rid of this regression line. Let's get rid of this altogether. But y equals 225,000 is way, way, way up here. That's kind of ridiculous. I could probably cut this down to thousands, but I don't know. I'll just do it. Let's just do it, and we'll find it. There it is. Then what I'm going to do is I'm going to graph the right-hand side, which is y equals 750,000 over 1 plus 0.45 raised to the 10x, raised to the 10x. Okay, and then I zoom in here, and this is allowing me to see where they intersect. Now, where these two lines intersect, the left-hand side and the right-hand side of my equation, is going to be the value. The x coordinate is going to be the value for k. So k, it turns out, is negative 0.106. 0.1, and I'm going to go out to the fifth decimal point because it's an intermediate calculation. So I will write that down. Then that means then I know the complete function is h of t, but the k is now that. So what I'm going to do is I'm actually going to come up here and call this now f of x. And I don't need this anymore. I'm just saving myself time here by putting this in now and making this equation raised to the negative 0.10611x. Like that. And then I can say, what's f of 15? Okay, 164,321. Well, I don't like that it's not exact, but you know what? I'll go with that right there. 164,321, f of 15. Make sure I put that in there right. But yeah, so that looks like it is. Now, it's not a bad idea to do this algebraically to figure out, how would you solve this for k without doing it using a graphing technique there. One of the things that you can do is you could just move this, you could move this denominator by multiplying it on both sides, move it over to the left, giving you this, and then dividing both sides by the 225,000. So this is going to make 750,000 divided by 225,000, right? It's 3.333. So we'll just do that right there. I'll take away 1. So that gives me 2.333. 0.45 raised to the 10k. What I'm going to do is I'm going to take the natural log on both sides with a base of 0.45. So I get 10k is equal to the log base 0.45 of 2.333. On your TI-84, you do have a log base function. I'm not going to show you where that is. You should know where that is, but I will show you here. There is a log base function. I believe it's down at, no, it's in the calculus section right there. There's a log base A. So you pull this up, you can put a base of 0.45 there and 2.333. You get that. And then you would divide that by 10. So take that number and divide it by 10. And there you go. That was our, I don't know why I erased it all, but that was our value there. 0.106 was our value for K. All right. And then once you have that, then you again are using your calculator to evaluate H of 15. Nicholas was saying, what happened to E in this equation? You are correct. I am not sure. I think that is a huge mistake on my part. I totally left that off. Thank you. So this was supposed to be E right there. Now, that being the case, I appreciate you letting me know that. Now, I'm not sure if I made that error when I was calculating K. I think I did. I think that I really did make that error. But that was what it was. I was raising 0.45 to that power. So that threw everything off right there. And that makes me wonder if they put that there, assuming that would be a common mistake that someone would make. If we have time, we'll come back to that. Okay. Thank you, Nicholas, for pointing that out. But the technique would still all be the same, right? Graphing it, finding K by the intersection of the left and right hand side, and then coming back and plugging in T 15 for the variable T. Okay, let's go to the next one. The problem number 8 I wanted to look at is trig modeling. How to handle RPMs when you're doing RPM to period. So here we have a rounding dartboard spins counterclockwise at a constant rate by a motor. The figure represents the board in the XY plane. When time t equals 0, the point A is on 5, 0. We're looking at it right there. it says if 180 rotations of the board have been completed in 1.5 minutes. So we have 180 revolutions that took 1.5 minutes. The point A is in the same position as it was at time t equals 0. Okay, which of the following could be used to model the x coordinate of the position of A as a function of time t? Well, here's the thing. The initial position is at 5, okay? And then it is going to be decreasing, right? The x coordinate. So it starts at t equals 0 at its maximum value because it's talking about the x coordinate. So as it begins to rotate, that x coordinate is decreasing. So this thing is most likely going to be modeled by a cosine function, because it would have to be looking like this, because it would be starting at its furthest distance away, but then moving towards 0. So when it comes up here, then its x coordinate is 0, and then its x coordinate goes negative as it's tracing its way down there. So just looking at these answers, take a look at these answers. For that, it looks like we do get rid of A and D, because cosine, it's not starting at a negative, right? Or it's not starting at the midline. So therefore, we get rid of those. So it all comes down to what's the B value right there. So as you know, B is 2 pi divided by period. So we have to know what the period is. And period is, in this problem, is a time. It's the time it takes for one revolution. And what you have to be careful of here is that time is in seconds, but they gave me these revolutions in minutes. So the first thing that I'm going to do is I'm going to take the 180 revolutions and divide it by 90 seconds, because 1.5 minutes is 90 seconds. So that means it's 2 revolutions per second. So when you take this, this is what's called frequency. It's revolutions per second. If you take that and flip it, that gives you the period. The period is 1 second for every 2 revolutions. 1 over 2 is 0.5, right? So it's 0.5, or 1/2 seconds per revolution. That's what we call period. It takes, for one cycle, it takes 1/2 of a second. So when you come over here to calculate this coefficient in your cosine function, you're going to be doing 2 pi divided by 0.5 as your period. That's going to give you 4 pi. 2 pi divided by 0.5 is 4 pi. There it is. Okay. And so we are going with answer B. All right. Good. Look at that. You guys are all over the fact that I left the E off. I am impressed that you caught that. All right. I think I'm going to try to give myself time to go back and wrap that up. Polar graph with a limited domain and quadrant question. Here they show you the g of theta is 3 sine 3 theta. And it says there's 4 points labeled A, B, C, D. If the domain is restricted, which of the following describes the portion of the given graph? Okay. So the way that you want to do this is you want to evaluate this function at the 2 endpoints of the restricted domain. So we're going to do g of pi over 2. So that would be 3 times sine of 3 times pi over 2. Okay, and that is sine of 3 pi over 2 is a -1. So the answer here is -3. So that means when I rotate pi over 2, I will be at an R of -3. That puts me at point C right there. Rotate pi over 2, but your R is -3. That means you count out 3 units on the back end of that rotation and you're ending at point C. Okay, so I'm already liking question D right here. But now I'm going to evaluate at the other extreme of the restricted domain, 2 pi over 3. So g of 2 pi over 3 is going to be 3 sine 3 times that. That's going to be sine of 2 pi. There. And that's 0. 2 pi over 3 times 3 is 2 pi. Sine of 2 pi is 0. 0. So you are back at the pole at D. So we're going with answer D. Pretty straightforward. Moving on, problem 10. You can expect a polar graph, increasing, decreasing R question, where they give you a graph, or don't give you a graph, they give you a function. And they just tell you, hey, this is graphed, but you can't see the graph because we're not giving you the graph and you don't have a calculator. Although you could graph it, sketch it, but you don't need to. Well, I am going to graph it. I'll show you how I'm going to graph it though. On which of the following intervals of theta is the distance between the point with polar coordinates increasing? Well, what I'm going to do here, students, is I'm going to solve this problem by graphing this in a rectangular system. I'm going to do -2 cosine 2x plus 1. I'm changing the order of the terms to make it look like it would look if I was to graph it in the xy coordinate system. Plus 1 means I've got a midline shifted up to 1. It has an amplitude of 2, so it would come up to 3, and it would come down to a -1. That's what the function would look like. It's a negative cosine, so that means it starts here. And the b coefficient is a 2, so I know that the period is 2 pi over 2, which is pi, which means the quarter periods are pi over 4. So this function would take on over one cycle. It's going to look like this cosine function, this negative cosine function, where this is pi over 4, a quarter period. This is going to be pi over 2. This is going to be 3 pi over 2. And this is going to be pi. All right, so now where, over what intervals is the distance between the point with the polar coordinates and origin increasing? Okay, well, this is going to be, this point right here is going to be pi over 6 right there, because that should be halfway between 0 and pi over 4. But not half, it's not going to be halfway, but it's going to be on the smaller angle, right? Because over here is going to be 2 pi over 3. So now I want it to know where it's increasing. So from 0 to pi over 6, this answer right here, the function is moving towards the pole. So the r would be decreasing. I mean, this is going to be the pole where the r value is 0. Or my y is 0. So it's not going to be this because I'm moving towards that. Now, pi over 2 would be here. Pi over 2 and then coming down to 5 pi over 6. If that's 3 pi over 2, no, that's not 3 pi over 2. If that's pi over 4, that's pi over 2. Sorry, that is 3 pi over 4 and then pi. All right, you guys didn't catch me on that one. I thought for sure I'd see somebody comment on that. But at any rate, if they went from 3 pi over 4, then this would be at 5 pi over 6. And again, this one, it's moving towards the x-axis, which means the r would be decreasing. So it's not going to be there. Okay, and then, but now look, it's saying from pi to 7 pi over 6. Here's pi. I don't think that's going to be it either because it would be moving towards the pole. Now, how about this one? 7 pi, yeah, so 7 pi over 6 to 3 pi over 2, it would have to be moving away up here. So this has to be my answer D. I'm looking at when it's moving away from the x-axis right there. So that's going to be my answer. So when you plot these functions in the xy coordinate system and you're trying to find out when the radius is increasing, you would have to be looking at a portion where as you're moving left to right, you're moving away from the x-axis. And that has to be it here. Because, let's see, this is going to be, yeah, so this is going to be over, yeah, we said this over here is where pi is. right here. So over here, that's going to be just past pi. That's where 7 pi over 6 is. So when you get beyond 7 pi over 6, then you're going to be the distance from the origin will be increasing. All right, let's go back. I did have some bonus ones down here, but I'm going to go back up here and finish this one off. I think I messed this one up from the get-go. So we will start back at the beginning. So we are going to plot y equals 225,000. And we'll plot y equals 750,000 over 1 plus 0.45 e raised to the 10k. Because remember, what we were doing is we were sticking in the ordered pair 10 comma 225,000. And that's going to be an x right there. So we're looking at where these intersect right here. So these two graphs, the left and right hand side, are intersecting at that point. So this tells me that our k, we're going to go back to the drawing board here. So that tells me that we were doing this, and we just solved that for k graphically and got an answer of 0.16458. Okay, we good there? I think we are, which just means then that what I'm going to do is I'm now going to change this to f of x, and then I'm going to come down and change my exponent to be 0.16456x. And I'm not graphing it at this point. I'm just using that now to be able to plug in the number 15. And I get 118,828. So yes, that is awfully close to that. And that's what we're doing right there. Now, if we round this to 165, that may explain maybe the difference if we did that. No, it just made it maybe not as close even. But so our answer here ends up being A. All right. And again, if you did this by, I think one of the things that I did here is I was showing you how to do this algebraically to solve for k, that is. So what we could do here again is switch this over to the left side by multiplying it on both sides. So it gives us e to the 10k. And then we're doing that was 3.33. So we take 750 over 225. We got this. We take away 1 on both sides. We get this. Now we're going to take the 2.333 and divide it by 0.45. And we get that. So now what we have is e to the 10k is equal to 5.1852. Now we take the natural log on both sides. So we will take the natural log of this number right here. Paste it right there. So that gives us 1.6458. Divide by 10, and we get our 0.16458 for k, which allows us to come back and plug that in for k and then evaluate it when t is equal to 15. That's how that works. Okay, John's asking a question. So would you be able to just write the equation and put f of 15? You would still get the same what if you have to do it h of 10. I'm not sure I got you there, John. I'm not sure what you're asking. I think that you have to first get that have to find out what that k value is. Or ask that question again. All right. Just a few minutes left. I'll show you what the other questions were. You may see an unfamiliar polar function, one that you're saying, wait a minute, I don't think my teacher showed this to me, right? This is 6 sine squared theta. Well, remember, you're looking at this. You probably could guess if it's a sine function. You might guess A just because it's symmetrical with respect to the y-axis. How does k equals point? All right, Ethan. Ethan wants to know why. How is k? Okay, thanks, Ethan. I'll get rid of that k. Thank you. Yes. I don't know why I put a k there. Okay. Anyways, so yeah, what you would do here is just plug in pi over 2, right? Because I want to know whether it's going to be up here. If you do put f of theta, if you put f of pi over 2, try some points. That's going to be 6 of sine of pi over 2, the whole thing squared. Don't forget, sine squared theta means sine theta, the whole thing squared. Sine of pi over 2 is 1. 1 squared is 1. So that means at pi over 2, you're at 6. So this point right here has to be on this graph. Because when theta is pi over 2, f of pi over 2 is 6. I think that's the only one that has the point at pi over 2 comma 6. So that's my answer. That was kind of easy. So that was one of the things. The h of 10 equals, sorry, I meant if you have to put the, this is John saying, so I meant if you have to put the h of 10, 223,000 on the graph to get the answer. No, I wasn't. I was doing, let's see. No, that's I think my point, right? You don't have to do it graphically. If you do plug this ordered pair into the function that they give you, I showed you these algebra steps here to get the k value. So you did not have to graph it. In fact, if you're not using Desmos, graphing's not a great option on the TI-84, although you could still do it, right? Because this is how you graph things on the TI-84. You graph, if you're solving an equation by graphing, you graph the left-hand side and you graph the right-hand side and you see where they intersect. The problem with the TI-84 is, most of you know, I'm sure, is that scaling your screen is the problem. Is that how do I get the scale on there? You got to go into the Windows settings to, or maybe if you know how to use the zoom feature, you can get it pretty quickly. But I find it to be pretty annoying, especially when it comes to how easy it is to just scroll in and out on the graph in Desmos. Anyway, so that was the one question. There was one other one, which was a complex number question. So make sure you can do complex numbers and go from rectangular to polar in the complex system. Don't have time for that tonight. Okay, everybody. Well, thank you for joining tonight. I wish you all the best of luck on Tuesday. And don't forget, make sure you got plenty of scratch paper. I assume that on the multiple choice section, you'll have scratch paper and not really a booklet, because you'll be reading the questions on the screen in Blue Book. And don't do things mentally, right? Write things down on scratch paper. You shouldn't be in such a rush that you can't work things out, quickly, smoothly on your scratch paper and not have to do a bunch of mental algebra. Other than that, thank you so much for joining. I am doing another live stream tonight for AP Calculus, and that's going to be at 9 o'clock. I'm going to be working through 2 FRQs that span all 8 units of the AP Calculus class. So if you're interested, join there, 9 o'clock. All right, everybody, have a good night and a good week ahead. And again, good luck on Tuesday.